This is section 10.1 on sequences, series, and sigma notation. A sequence is an ordered list of numbers. For example, 2, 4, 6, 8, 10. Each number is known as a term. We have the first term, the second term, the third term, and this term right here is the first term. We call it a sub 1. The 4 is the second term. We call it a sub 2. So a sub 2 is 4, a sub 3 is 6, a sub 4 is 8, and so on. A finite sequence contains a finite number of terms. It does not go on forever. In this case, we have 5 terms. An infinite sequence contains an infinite number of terms. When we have 2, 4, 6, 8, 10, comma, dot, 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 that signifies that this sequence goes on forever. A sequence can be defined explicitly using an explicit formula. An example, an explicit formula for an arithmetic sequence is a sub n equals a sub 1 plus n minus 1d. It's a recipe to find each of the terms. And what's nice about the explicit formula is you can jump to the 10th term if you'd like. In this case, a sub 10 is equal to 3 plus 10 minus 1 times 4. So the 10th term is 9 times 4 is 36 plus 3 is 39. Example 1, find terms of sequences. Find the next 4 terms of the sequence, 2, 7, 12, 17. With each of these, we're adding 5 to get the next one. So we have 22, 27, 32, and 37 is the next 4 terms. Each time we add 5. B, find the next 4 terms of this sequence, 2, 5, 10, 17. Each of these is one more than a perfect square. So we have 1 squared plus 1, 2 squared plus 1, 3 squared plus 1, 4 squared plus 1. So 5 squared plus 1 would be 26, 6 squared plus 1 would be 37, 7 squared plus 1 would be 50, and 8 squared plus 1 would be 65. Find the first 4 terms of the sequence given by this explicit formula. A sub 1 is equal to 2 times 1 times negative 1 to the first, which would be negative 2. A sub 2 is equal to 2 times 2 to the negative 1 squared. That's equal to 4. A sub 3 will be 2 times 3 times the negative 1 to the third, which is negative 6. And then a sub 4 is equal to 2 times 4 times negative 1 to the fourth. And that's equal to positive 8. And notice with negative 1 to the n, this will go negative, positive, negative, positive. Find the next 4 terms of each sequence. 32, 16, 8, 4. In this case, we're getting the next one by dividing by 2. If we take 4 divided by 2, we get 2. Then divide by 2 is 1. Then we get 1/2, and finally 1/4. With 1, 2, 4, 7, 11, keep on going. Looks like we're adding 1, and then adding 2, and then adding 3, and then adding 4. This would be plus 5, plus 6. So to add 7, we would get 29. 8 would be 37. 9 would be 46. And 10 would be 56. Find the first 4 terms of the sequence given by this explicit formula. A sub 1 is equal to 1 to the third minus 10, that's negative 9. A sub 2 is 2 to the third minus 10, that's 8 minus 10, that's negative 2. A sub 3 will be 27 minus 10, that's 17. And then a sub 4 is equal to 64 minus 10, that is 54. Sequences can also be defined recursively. Recursively defined sequences give one or more of the first few terms and then define the terms that follow using those previous terms. The formula defining the nth term of the sequence is called a recursive formula or a recurrence relation. The most famous is the Fibonacci sequence. The first term is 1, the second term is 1, and then you get the one you want by adding the previous 2 terms. So then we get 2, which is 1 plus 1. Then 2 plus 1 is 3. 3 plus 2 is 5. 5 plus 3 is 8. 8 plus 15 is 13. and so on. Find the fifth term of the recursively defined sequence where a sub 1 is 1 and a sub n is, take the 1 before it, add 2 times the term you're on, and then minus 1. A sub 2 is equal to the 1 before it, which is 1, plus 2 times 2, and then minus 1. So we have 1 plus 4 is 5, minus 1 is 4. A sub 3 is the 1 before it, which is 4, plus 2 times 3, minus 1. That's 10 minus 1, that's 9. A sub 4 is 9 plus 2 times 4, minus 1. That's 17 minus 1, 9 plus 8 being 17. That's 16. And a sub 5, the fifth term, is 16 plus 2 times 5 minus 1. That's 26 minus 1, that's 25. Find the sixth term of each sequence, and I can see I have the answer already, but let's try to get that answer of negative 96. A sub 1 is 3, and a sub n is negative 2 times the one before that. So a sub 2 is negative 2 times 3, which is negative 6. A sub 3 is positive 12. A sub 4 is negative 24. A sub 5 is 48. And a sub 6, if we take negative 2 times 48, we get the negative 96. In 2b, a sub 1 is 8. A sub n is 2 times the one before it, but then minus 7. So a sub 2 is equal to 16 minus 7 is 9. A sub 3 is 18 minus 7, which is 11. A sub 4 is 22 minus 7, which is 15. And a sub 5 is 30 minus 7, which is 23. And then a sub 6 is 2 times the one before, which is 46. 46 minus 7 is 39. In Lesson 1.3, you examine the end behavior of the graphs of functions. You learn that as the domains of some functions approach infinity, the ranges approach a unique number called a limit. So if we get a graph, and as x shoots out to infinity, if the graph levels off to, let's say, this was leveling off to 1, we would say the limit is equal to 1. Limit is, let's say, x approaches infinity. If a sequence has a limit such that the terms approach a unique number, like in our example 1, then it is said to converge. If not, the sequence is said to diverge. Determine whether each sequence is convergent or divergent. Letter A. A sub n equals negative 3n plus 12. If you click mode, we can turn our calculator into a kind of a sequence generator. And then go down, instead of connecting all of our points, we'll just make each of the points dotted. Then when we click y equals, we see that the n minimum is set to 1, which means we're going to plug 1 into this formula to start out with. We'll have negative 3 times 1 plus 12, that's going to be 9. So we've plugged 1 in, and our value, y value, is 9. So negative 3n plus 12. And when we go to graph that, we can see that this function just keeps going down forever. It's not going to level off. We say that this sequence diverges. Let's look at letter A. A sub 1 is 36, and a sub 1 is negative 1/2 a times n minus 1. We're not going to be able to use a calculator for this because this is going to be recursive. So 36 times negative 1/2, so a sub 2 is equal to negative 18, and then a sub 3 is equal to 9, then a sub 4 is equal to negative 9/2, and then a sub 5 is equal to 9/4, and so on. These values are getting smaller and smaller and smaller. As a matter of fact, they're approaching 0. So this one converges. Let's look at example C. We have a sub n equals negative 1 to the n times n over 4n plus 1. If you hit y equals, we can enter the function in. We have negative 1 raised to the n times n. We'll close the parentheses for the top, and then divided by parentheses 4n plus 1. Now if we look at the first value, when we plug 1 in, a sub 1 is equal to negative 1 to the 1 times 1 over 4 times 1 plus 1. Now that's equal to negative 1 over 5. So we're looking at some pretty small values here. I'll go to the window, and for x max, let's start at 0 and go to, let's say, 30. And for the y minimum, we can do negative 1 and 1 for this one. Let's graph. Oh, let's see how it stopped. If we go back to window, we said, well, just plot it for 1 to 10, for n from 1 to 10, but then we made our graph go to 30. So if we make this go to 30, then it should go to the end of the graph. Now look how it's bouncing from negative to positive to negative to positive. That's because of the negative 1 to the n. When n is odd, it'll be negative, and when n is even, it'll be positive. But we want to find out if this is converging to a value. And in this case, 0 seems to be right in the middle. We want to see if this is converging to 0. So let's trace it. And you can see the y values are going negative, positive, negative, positive. But the one thing we notice is that the y values are actually getting farther from 0. So this is not converging to 0. As a matter of fact, each point is a little farther from 0. So this one is diverging. In 4a, we have a sub n equals 64 over 2n. So let's go to our y equals, clear this. We have 64 divided by 2n. I should put parentheses in the bottom here. 2n. And let's see what our first value would be. Our first value is actually 32. 32. Our second one would be 16. And our third one, 64 divided by 6. So that's 32 over 3. That's somewhere around 10. Let's go to our window, and let's go from 1 to maybe 30 would be fine, and then 0 to 30, and then our y maximum. Where's our y max? Right here. Let's make that 32, and make our y minimum negative 1, because this is never going to be negative. When we graph, we see that this function is going down, 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 and it seems to be approaching 0. So this one converges. A sub 1 equals 9, a sub n equals a sub n minus 1 plus 4. So we take the previous one and we add 4. So we have 9, and then 9 plus 4 is 13, and then 4 plus 13 is 17, and then 21, and then 25. And this seems to be shooting up to infinity. This one is diverging, or diverges. A sub n equals 3 times negative 1 to the n. This is an explicit formula, so we can put this into the calculator. We have 3 times negative 1 raised to the n. Let's go to our window, and let's make the y maximum 3, and we'll make the y minimum negative 3. Actually, let's make it one more. How about we go 4, and let's go with negative 4. And notice when we graph this, it's just going, if we plug 1 in, it's negative 3 and then 3, and then negative 3, then 3, and let's trace. And see how it's just bouncing? The y is just bouncing from negative 3 to 3. Now, a function cannot converge to two different values. So this one is diverging. Diverges. Series. A series is the indicated sum of all of the terms of a sequence. Like sequences, series can be finite or infinite. A finite series is the indicated sum of all the terms of the finite sequence, and an infinite series is the indicated sum of all the terms of an infinite sequence. So a finite sequence could be 1, 3, 5, 7. The series is take that sequence and just add those numbers together. We'll have 1 plus 3 plus 5 plus 7 plus 9. So there's your finite sequence and series, and with the infinite, we just put the plus dot 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 or comma dot dot dot, which indicates this goes on forever. The sum of the first n terms of a series is called the nth partial sum and is denoted S sub n. The nth partial sum of any series can be found by calculating each term up to the nth term and then finding the sum of those terms. So if you want the sum of the first three terms, you'd write S sub 3. So that's a partial sum of the first three terms. Find the fourth partial sum of a sub n equals negative 2 to the n plus 3. So the fourth partial sum, which is equal to negative 2 to the first is negative 2 plus 3 is 1. And then plus, let's plug 2 into the n, that'll be 4 plus 3, that's 7. And then when we plug 3, that's going to be negative 8 plus 3, that's negative 5. And then the fourth term, when we plug 4 in, we get a positive 16 plus 3, that's 19. So we have 8 minus 5 plus 19, that's 3 plus 19, that's equal to 22. Find S sub 3 of a sub n equals 4 over 10 to the n. That's equal to 4 over 10 plus 4 over 100, or 10 squared. And then plus 4 over 10 to the third is 1,000. And we can get that here on the calculator. 4 divided by 10 plus 4 divided by 100 plus 4 divided by 1,000. And we get 0.444. Find the sixth partial sum of this find the sixth partial sum of this recursive formula. Sixth partial sum. So a sub 1 is 8. So we have 8, and then we have plus half of the previous term. So that's going to be 4, 2, 1, and 1 half. There's 1, 2, 3, 4, 5, and then plus 1/4. On 5a, we find the sixth partial sum of this recursive formula. We start out with 8, so the sixth partial sum is 8 plus, and then we take half of the term before. So that's going to be 4 plus 2 plus 1 plus 1/2 plus 1/4. So we have 12 plus 2 is 14, 15 and a half, so we have 15. That's going to be plus 1/2 plus 1/4, which is 60/4, plus 2/4 plus 1/4, which is 63/4. Since an infinite series does not have a finite number of terms, you might assume that an infinite series has no sum s. This is true for the series below. If you have an infinite sequence 1, 4, 7, 10, the infinite series is 1 plus 4 plus 7 plus 10 plus keep on going. And the sequence of the first four partial sums are 1, 5, 12, 22. That means the first partial sum is 1. The second partial sum is 4 plus 1, which is 5. And then you add 7 onto 5, you get 12. And then if you add 10 onto 12, you get 22. This is going off to infinity. The partial sums are shooting off to infinity. However, some infinite series do have sums. For an infinite series to have a fixed number s, the infinite sequence associated with this series must converge to 0. Notice the sequence of partial sums in the infinite series below appears to approach a sum of 0.1 repeating, or 1/9. So the infinite sequence could be 0.1 and then 0.01 and 0.001. And notice how each of the next term is getting smaller and smaller and smaller. So we're adding less and less and less. The infinite series is, of course, add those up. And then the sequence of the first three partial sums is 0.1, 0.11, and 0.111. And notice how each time you just keep adding another 1. Well, that's converging to 0.1 repeating, or a fraction of 1/9. We will take a closer look at sums of infinite sequences in Lesson 10.3. Series are often more conveniently notated using the uppercase Greek letter sigma. A series written using the... Let's redo that. Series are often more conveniently notated using the uppercase Greek letter sigma. A series written using this letter is said to be expressed using summation notation or sigma notation. For any sequence, a sub 1, a sub 2, a sub 3, a sub 4, the sum of the first k terms is denoted by, we have the sigma notation, n equals 1 to k of a sub n. So you plug 1 in, and then you plug 2 in, and then you plug 3 in, and so on. In this notation, the lower bound indicates where to begin summing the terms of the sequence, and the upper bound indicates where to end the sum. So we could start from, let's say, 1 to 10, or 1 to 20. If the upper bound is given as infinity, the sigma notation represents an infinite series. So if infinity is on top, this means we have an infinite series. Sums in sigma notation. Find each sum. So letter A. This represents the sum of a sequence of numbers. And you get that sequence of numbers by plugging 1 in. So we get 4 times 1 minus 3, that's 1. Plug 2 in, that's 8 minus 3, that's 5. And then you keep on going. Plug 3 in, 12 minus 3 is 9. Plug 4 in, 16 minus 3 is 13. And finally plug 5 in, that's 20 minus 3, that's 17. So 1 plus 5 is 6, plus 9 is 15, 28, we have 45. In letter B, we plug 3 in to begin with instead of 1. That's 18 minus 3, that's 15 divided by 2. So let's say 15 halves, plus. Plug 4 in, 24 minus 3 is 21, so 21 halves. Plug 5 in, 30 minus 3 is 27 halves. Plug 6 in, we get 36 minus 3, that's 33 halves. And then finally we plug 7 in, that's 42 minus 3, that's 39 halves. So 15 and 21 is 36. 36 and 27 is 63. 63 plus 33 is 96. And then 96 plus 39 is 135 over 2.